So I think one of the most fascinating questions out there at the moment, we've talked a bit about exoplanets, but do we actually understand how the solar system formed? I mean, as I understand it, you begin with the cloud, which has already been contaminated by ejecta from an exploding star, and the dust grains, and the cloud collides into other clouds and cools down, gets denser and massive, gravitationally unstable, collapses, spins up as it collapses by conserving angular momentum, and eventually dust grains coalesce, get bigger and bigger, and a spinning, flattened cloud forms, full of tiny dust grains. And maybe the center can form the proto-sun. But how on earth do the planets form? Do we have any idea?
So, first of all, I don't claim to know everything about this area, but I know a few things. So, yes, indeed, the way that we think planets form, they are intimately, typically related with the formation of a star. So you form a star, and you form a disk around this star. And in this disk, you have gas and you have dust. The idea is that you first form the things that are rocky. And I believe that simulations know how to deal with dust particles sticking to one another and forming, small things. I think that simulations are also okay from a certain scale up. I think that there is still unclear region that bridges, the rocks and things to kilometer size things. That, I think, is a region where the physics is not entirely clear.
So is it fair to think, these dust grains actually are coated with ices, for example, we know that. And so you have these icy mantles around the grains, and they coagulate, they get bigger. So when they collide, it's a bit like snowballs, colliding, being squashed together, and they could imagine sticking together. So that early stage of building up to maybe even meter-sized snowballs with rocky cores, I could imagine. But then the next step.
Right. So that's, I think, a step where we don't really know. However, if you allow yourself to say, okay, even though I don't know how to do that, nature does, and then you start to form these planetesimals, which then, those collide and form bigger things until you actually form a core that, is something like Earth size or thereabouts. And at some point, that thing starts some runaway accretion of gas from that same disk onto it. And that's how eventually giant planets form. And the terrestrial planets probably form once there is no gas anymore, to accrete on top. And, that's when you form these rocky planets that we find. So all of this, I should say, is what is known as the core accretion scenario, which says, you start from dust grains, you make these things. There is a stage in the middle which is not entirely clear, but you at the end form something that is, the size of like a little planet. If there is still a lot of gas, it will go to a runaway accretion of gas, and it will form a giant planet. If there is not much gas, it will stay as a rocky planet. There is a competing theory about formation of gas giants, which is really a disk instability type thing, which says that you actually have a disk that becomes unstable, and parts of it basically collapse directly to form these giant planets. So it's not the core accretion type thing, but it's a disk type instability that forms. Now, that's not how you probably form the rocky planets anyhow, but it is perhaps a way to form giant planets, right away.
And is it fair to say that, these hypothetical planetesimals, that they're basically the asteroids, the asteroid belt, they're the vestiges of these things. And so this gives us some confidence in this reasoning.
Yeah, I think, well, the asteroid belt, is at a place where there is also a giant planet nearby, in that case Jupiter in our solar system, which in some sense prevented a planet from forming in that region. And what is known as the snow line in our solar system, which is the place, outward of which, things are cold and, and rich in water, basically, and inwards from which it's dry, actually falls in the middle of the asteroid belt in our solar system. And yes, now this asteroid belt, believe it or not, may actually have some importance for the appearance of life, because asteroids are thought to have brought to Earth all kinds of things that maybe Earth would not have had otherwise. For example, Earth formed most probably in the dry part of the disk, of the proto-solar disk. And so it has very little water by mass, but it has large surface oceans. And those were most probably brought to Earth by something, collision of asteroids, maybe some comets, but asteroids may have brought much of that water. And if we think that the existence of that water on the surface was essential for life, then that may be that. Other things that have been suggested is all kinds of heavy metals, which when the Earth formed, sort of basically settled inwards and were absent from the crust, but maybe have been brought by asteroids as well. And some people even go so far as to say that the initial molecules that started life were brought by some asteroids to Earth. So having something like an asteroid belt may actually be, I don't know if essential, but important for life to start.
But as far as the origin of the planets, I mean, going from interstellar dust grains to more macroscopic, tinier objects, gigantic grains, if you like, tiny rocks, up to asteroid-sized objects, that's just coalescence somehow.
Yeah, I think
and,
so. And collisions.
And collisions. And
yes.
Could we think of the asteroids as being the relics of that process, the survivors?
Yeah,
I think not merged together.
Yeah. I think they are the equivalent of all kinds of debris disks and things that we find around other planets.
That adds some confidence to this
scenario.
Yes,
that's right.
Right. And so, is it natural then to always have gaseous giant planets along with the inner rocky ones? Is that a generic prediction of for planetary systems elsewhere in the universe?
I don't know if that, I mean, we know a number of solar systems. We know places where we only know one planet and so on. Usually, and plus, planets undergo migration through disks, so we know some places, it's only a few percent, but where giant planets are even close in. When giant planets are close in, typically you don't see the smaller planets in that region because maybe they have been thrown away or swallowed by the star and things like that. When the planets are farther out, you can have the smaller planets, rockier planets in the middle. So I think that it is sort of generic, but it depends a lot on what were the conditions when the last migrating planet did its thing. Because as this gas and dust disk evolves, it is also being at the same time evaporated by radiation from the central star. And so, for example, you can have a situation which probably even happened where giant planets form outside the snow line, and they migrate through the gas disk, and they migrate all the way into the star, and they keep doing that. They form outside the snow line, migrate all the way in, but at the same time, the gas in the disk is being constantly depleted, so that at one point, you have a giant planet that maybe migrated or not a little bit in, but there was no gas left, and it just stayed where it was there. And those conditions change from system to system. So you're going to find, quite large variety of these.
So let me understand, why does migration occur? Is it because of collisions with smaller objects that the object loses energy and then...
It loses energy because of its interaction with a gas. Yeah. I mean, well, there are things, I don't want to get too technical. There is type 1 migration where the planet opens a gap around. There are two types, type 1 and type 2. One in which the planet opens a gap around it, and one in which it doesn't. And that depends on the size of the planet and its gravity. But in both cases, it has to do at the end with the interaction of the planet with other things.
Okay, so this is only in the very early stages of the solar system when it's gas. There's a lot of gas in the
when there is
disk.
still gas, yeah, right.
Okay, so how long does that phase last? Not very long, I imagine.
No, not very long. And it depends also, again, it depends on the environment, because if there are, for example, very bright stars in the neighborhood, as for example there seem to be in the Orion Nebula and so on, then those very bright stars, they can evaporate those disks rather quickly on timescales that are short, that maybe even you cannot form giant planets to begin with, because there just isn't gas there.
And when we look at the moon and we see this amazing record of cratering because of its lack of atmosphere, does that tell us about this early gas-rich, planetesimal-rich phase of the solar system? Can we deduce conditions from studying the moon, the record on the surface of the moon?
Well, I think the record on the surface of the moon is more related to this phase of bombardment that happened during that time.
But the bombardment came from the nebula, from the protosolar nebula.
Right. So it does tell us something. And I'm aware of one paper that I remember. This has been a while ago, and I don't remember the details. But I think that if one studies actually the distribution of sizes of, not of the craters themselves, because when something hits, it generates a bigger crater than the size of the object. But people can do simulations and try to correlate size of craters with size of impactors. So I remember this paper that tried to calculate the distribution of sizes of impactors on the moon, and showed that it is actually the same size distribution to the extent that you can compare them to the asteroids. So I found that quite remarkable, that you look at the asteroid belt and size distribution, and you look at the size of the distribution of impactors on the moon, and they appear to be coming from the same distribution.